I will talk about cellulose that I think should be of interest to this community, and then a series of work that we've done with using metal cations to modify cellulose. And some of the work was already done at the times when I was at Chalmers, and we still keep going. So it's a continuation of activities. And the motivation here, so kind of cellulose is a great substrate for a lot of things, but it's not a very active one. So it's usually more in the passive role of a support substrate or support material, filler, and so on. So here the motivation is to use metal cations to change its properties or functionalize it to make it a little bit more active. And of course, there is a lot of interesting applications what the modified celluloses can be good for, but I have been focusing more on the how to modify them, what is the loading, and this kind of phenomena related to the modification itself. So the main motivation is to make cellulose more active. And and another maybe motivation then with this cation modification, so we're using very simple approach. So it is to have an easy way to alter alter properties in an easy way for many purposes. And then for this objective of having an easy way to modify for many purposes, so these many purposes we cater with having a selection of different cations that we can introduce to cellulose. Regarding the properties that are of interest, so we're looking into rheology, optical properties like the refractive index and changing it, electron contrast, and as well as some magnetic functionality. These very much depending on the cation that you choose for the modification. And the system is very simple and it is not new, so to say. So it's to utilize a functional group like a carboxyl group or sulfate group and exchange or sacrifice a proton and exchange a cation there. And there's a lot of work that has been already done to this. So using a sodium countercation for sulfated celluloses is a common practice to hinder the hornification or aggregation of the material. But also some other cations have been quite often introduced, like potassium or lithium. But here, so I will focus on three different works, but two are related to the selection of the cations. So in the first one, we were interested in looking at the alkali metal cations and the whole first group and the row of it. So the lithium, sodium, potassium, rubidium, and cesium. And kind of what you could think of as a motivation is that when we go down the group, the size of the let's say the size, so to say, of the cation increases. So this can then, or I was imagining at least in the beginning that this can have consequences to the optical properties, for example, on the refraction of light. You can see here some illustration of it. It's not any modeling, it's just a simple drawing. And then another set of selection of cations that we have worked with is then a little bit more special one. So in the group of lanthanides. So these are elements or substances that do a lot. So there's a lot of interesting optical and magnetic properties like luminescence or any kind of emission of light. And here for our work, we have chosen some of some of the suspects like europium, gadolinium, and dysprosium. But in the literature, there's also some others like very often europium, but also some other lanthanides that have been introduced in the context of cellulose. Then, of course, there's more than just the cation exchange. There's also the simple blending into cellulose dopes and forming fibers, films, composites, and in that way incorporating the active cation or active component into the cellulose matrix. So yeah, the basic objective is simple. For us to use a functional group where we can substitute a proton with a cation, choose that with the interest of the functionality in mind, and then focus on the properties that we can get. So first, let's look at the first group, alkali metal cations, and kind of the simple or the procedure that we use for the cation exchange. And this was already done published 2022. We had Patrick who was doing most of the experimental work. So the cation exchange is done with salts of the cations in an aqueous system, where we protonate first. Maybe something very an important detail or important information to notice is that all of this work here in this presentation is now using these sulfate half ester containing cellulose substrates. So we are focused on the sulfated systems and introducing the cation to that. So the procedure is to protonate, then expose the substrate to an excess of the target ions or the cations, neutralize and dialyze, and then analyze how much of the cations were we able to introduce. Maybe like the more, let's say when cation exchange is used, typically maybe it's more for analytical purposes, and then very often there's a need for ion exchange resins to do a really, really good job. But here, since we're doing a modification, we have tried to avoid using that and do a simple version and still be able to achieve a high enough level of substitution. And here's some results for the first group, alkali metal cations. So you can see here the molar ratio of the metal to the sulfur. So now this was the sulfated substrate. So contrasting how much of the metal cation has been introduced in the molar ratio to sulfur, which represents then the number of the sulfate groups. And here is first just the sulfur. So it doesn't. It has now the sodium there to begin with, and then we have the protonated form, and then the series of the lithium, sodium, potassium, rubidium, and cesium. And we can see here these inclusion levels with the excess of the cations available and the levels that we can achieve. So we firstly see, let's say, maybe when we look at the cations here, so from the lithium to the cesium, the lowest level that we achieve is with the lithium, and the highest level with the rubidium. So quite good inclusion levels from 76% to 89%. Maybe some things to note is that when we do the protonation, so we still have quite much of the sodium that we start with left. So the protonation is difficult with this system to achieve fully. However, then so our starting material is in the sodium form. When we exchange back the sodium form, we almost get to the similar level as in the starting material. phase. Maybe the reasons behind the different inclusion levels are yet for me to resolve, but yeah, within this series we can get quite high levels of substitution. Then of course here it's a little bit of a simplified system because we don't vary, for example, the functional group content, which could be an obvious way of then affecting our parameter to change the inclusion level. Here is the same information in a more dry format, so the elemental composition. So here you can see the same suspects. So the first group cations on the cellulose substrate and the levels of the composition of the different substances in milligrams per kilogram. And here on the highlighted, you can see always the target, the amount of the target cation and how much we have been able to introduce it to the system. And here you can see that maybe the challenge of the protonation with the simple hydrochloric acid treatment, that we still have quite a lot of sodium there to begin with, or to continue with. However, it does not seem to hinder that we are able to then also introduce the other cations in. So this leads us to conclude that, okay, it's a very simple way. You have your protonated cellulose substrate with a functional group. You expose it to an excess of a cation. You neutralize the pH and you dialyze, and you have a modified material at hand. And then we looked at in that list of the properties, or the target properties. What I would like to share today is some rheological properties. So here you can see the dynamic moduli with respect to strain amplitude, and this is now here telling a story of the either liquid-like or gel-like behavior of these suspensions or dispersions of the modified celluloses. And here you can see the, let's say, just the protonated, so the non-modified version of the cellulose material. And here we observe the G prime and the G double prime, so the storage modulus and the loss modulus. And we can observe that with our non-modified version, we have a liquid-like behavior. So the loss modulus is higher than the storage modulus. And then we have another set of behaviors here with the modified celluloses, where we see more like a gel-like behavior, where the G prime is higher than the G double prime. There's also some let's say weak strain overshoot here in this strain amplitude region, which then reflects the network properties of the material. So here we can say that we have altered the rheology. It does not seem to follow, or it did not seem to follow the order, for example, of the size of the cation, rather than just grouping with a cation modified and non-modified to two different groups. Then we also looked into the loss tangent, and there we could see again like that the non-modified version is very different from the modified ones. However, there is an exception always noticed with the potassium modified, which is then more, let's say, liquid-like rather than gel-like in comparison to the other series. And quite interestingly, when looking into the literature, it's also something that is sometimes reported, that the potassium as a countercation for cellulose is having a, so to say, disruptive or dispersive property rather than which is unlike than the other cations. So in a way, we are observing something that also has been observed by others, which is nice. And then we also looked at the rheology. So I have worked together with Roland from Chalmers for a long time, and he has developed this way of looking into structuring of cellulose by observing with the polarized light, the orientation patterns. And then we of course looked at also these systems with that. And how you read this picture here or this presentation here is that you can see here are materials that are observed under the polarized light microscope, and we are looking at them in with respect to different shear rates and how do they behave. And what we are looking to see is either to see or not to see this kind of a wait, where is my pointer here? This directional orientation. And if we see this is giving us an indication that the system is able to orient with respect to the shear, and there is kind of a biphasic behavior with respect to that. If we don't see it, then we would consider it more of an isotropic system. So then we can see here with our protonated system an alignment. And then with the, let's say with the lithium and sodium systems, we can see it already early on with lower shear rates, and then definitely in the high shear rates. With the potassium, we do not see orientation. With the rubidium and cesium, we see it, although with the cesium, that's the largest cation. We don't see it as clearly as with the others. So again, also with this kind of structuring perspective, the potassium behaves differently from others. So with this series that we did with the alkaline metal cations, we see that the potassium modified stands out rather than that we would have some kind of a behavior that would correlate with the cation size. And now here is a summary of some of our observations with the rheology, so the loss tangent, the kind of a color of this cross that you saw already, and the estimated phases, so either biphasic or isotropic. Then we of course have done quite a lot of other investigations regarding the properties, optical properties of this material, but those are still in the making, so to say. Then we can go for the more special cations, so the lanthanides that I already introduced to you. So we can find them here if we look at the periodic table in the bottom part. And with this work, we were more looking into giving a more spectacular properties to the cellulose, kind of having cations that could do more than just the first group selection. And here we had already what I introduced. We had europium, we had dysprosium, and we had gadolinium. And with the again with this introduced with the same kind of a procedure, so using the chlorides that we can introduce in an aqueous system. Europium and dysprosium were selected for their characteristics, red and yellow luminescence when they are coordinated with ligands. And then with the gadolinium, we selected it for its known magnetic properties or ability to alter magnetic behavior or behavior in magnetic fields. And with this, we did the similar type of a procedure to introduce them in a dispersion. And you can see here the same kind of an analysis of the inclusion level. So here is the cation to the sulfur in this is in an atomic ratio, But yeah, we had the elemental analysis. Then we did also XPS and EDX analysis. We can see that the inclusion levels, again with an excess exposure, are much lower than with the first group. Again, there is some outstanding questions related to how to increase this, what is the specificity, what is the reason for the differences in the inclusion level. And here with this analysis, you can see elemental composition with respect to XPS, so you can consider that the elemental analysis will probe the cations or the lanthanides wherever they are, and with the XPS we are more on the surface. So we can see that the detected levels of the inclusion levels seem to be higher with the XPS rather than with the elemental analysis, but because it's a surface sensitive method or more surface sensitive method, so then we can think of that we could think that the inclusion is then on the surface of the crystals, which makes perfectly sense because we wouldn't assume that these salts are able to penetrate in the very impermeable cellulose nanocrystal substrates. Yeah, okay, so with this I also share similar type of a presentation of the rheological properties. We could see that here are reference of the unmodified, now it was a sodium CNC, but let's say the concentrations were different, a little bit lower from the study that was done with the alkali metals. So here we had a predominantly viscous behavior with unmodified ones, and again we have a modulation of the rheological properties of this material when we introduce the cations, in this case the lanthanides. In Roland's investigations, so there was no evidence of the structuring using this polarized light microscope setup, which is quite interesting as well. And the network behavior, we can say that it works a little bit differently, so we can see less of this strain overshoot here in this region with the alkali metals than with the lanthanides than with the alkali metal cations. Okay, we then were analyzing quite a lot of different kinds of properties. So Panos, who was doing this work, so he was very busy in the lab finding out what kind of properties could we observe and how could we do that, and what could these very special cations do to us. With the europium system, so we could identify red luminescence emission. With the dysprosium, there was always a little bit of challenge that it didn't do much. The question then is, or I think the outstanding question is then in the coordination environment. With the gadolinium, so then we had collaborators who work with the magnetic resonance imaging, so we could see that there's very much shortened relaxation times, which then gives an implications that they are active substances in an MRI. If they could be really used for imaging, of course, then it's a matter of a lot of other types of investigations that have to be done. However, this is a property that we could verify. And then the latest work that we have done is then apply some of this modification method of some of these cation in analysis of cellulosic materials. So this is more recent from last year, mainly driven by Daniel in Graz, to use the metal cation for labeling of cellulose, and then its analysis or visualization of its structure or the properties. So here the idea behind is that we know that the metal cations, they should bring a higher resolution in the electron microscopy techniques. So we chose here the cesium-1, cesium modified cellulose, and then Daniel's method of high resolution cryo TEM. Kind of initially, I was interested in figuring finally out where the sulfation takes place in these substrates, but there's maybe much more that can be figured out, or much more than this kind of a labeling can provide us. So we wanted to probe the location of the cesium and use that to get information regarding the location of the sulfate half ester groups, and why not also of the structure of the cellulose. So here you can see an TEM visualization of a very typical one of the CNCs on a carbon substrate. We can see that they bundle, so they are very much aggregated, or bundled. I guess that's the best way to say it. And then we can identify that within these bundles there are always some of them together. However, they're quite aligned then within these bundles. And then looking into this within the EDX, we can identify that, okay, the cesium is there. We can also identify the sulfur there. So this will give us a good way forward to go ahead with the analysis. And with this instrumentation or equipment that Daniel is using, so it allows atomic resolution. And then we also have this or annular dark field imaging mode, or high angular dark field imaging mode, which is especially good for heavier elements. So here you can see now a zoom in. I think it's somewhere around here with the HAADF, where the bright spots are indicating the locations of the cesium in this system. Yeah, so this is particularly suited for these heavier elements like the cesium. Then, of course, this still looks like a little bit of a cryptic one. So there's more analysis that one should do to get to point the locations of the sulfate groups, or do more, draw more conclusions regarding the structure. So wait, I think it's then here. Yes, so here is a little bit of more on that. So here you can see a zoom in with the high angular dark field image here with the 10 nanometer scale bar. And we can see here some CNC orientation. And then even a higher magnification and some image analysis, we can start to see here the CS atoms and the clusters that are now highlighted with this greenish color. And kind of we can see that these cesium atoms are visible, and they seem to be aligned, like along or parallel to the chain. So we are now looking into the cellulose crystals aligned in this direction. And with the analysis, it was also what Daniel did. We could see that the diameters of these spots are some 100 to 150 picometers. So we have this kind of a distinct pattern that emerges, and then with image analysis or AI-guided image analysis, we can even identify we can identify even more. Let's say we can bring up even more these dots that are now distinguishing the locations of the cesium atoms, or cesium ions. So we can see them here in the middle with the red dot. So the background is with blue, and then our our target subject is with the yellow and the red dot. And so here, what is now kind of what we should then keep in mind when we think about what can we conclude from this is, so we have these cellulose nanocrystals. They are sulfated. With our analysis of the sulfur content, then we know how much of the sulfur there is. We can calculate from that we can estimate from that how much of the surface, for example, should be covered with the sulfate groups. And in this case, we know that, or we estimate that it should be approximately 15%. Then we also think that where is the sulfate group? So we are thinking that it's in the C6. And then we know that in this case, in almost every of the sulfate groups, there should be a cesium if our analysis is correct from the beginning. So then in a way, wherever there is a cesium, we could think that that's indicating the location of the sulfate group. Okay, here, yeah, what else can we say about this? So we can see these kind of cesium highways here. So this is kind of giving us some kind of a rather strong suggestion that they are positioned on the faces of the CNC crystallites. And the patterns are rather regular. And then if we think about the density, so if we think that they would be around the crystals, then there should be some accumulation of them on the edges of the crystals. But that was never what we did not observe it in this case. So it's kind of giving some idea that there is depending on the location, there's a locality dependence on where the sulfate groups are located. Okay, what Daniel then was also working with this is to use these images and use these locations of the cesium to calculate or observe what kind of distances between them we can observe. And typically, he could identify values between 3 to 7 angstroms, depending on the direction that they are observed, and then relate that to what would we expect there to be with regards to the cellular structure. You can go and maybe look into more details of the simulation that he did and these estimations in the paper that was published. So that was what I wanted to share about the metal cation modification of cellulose substrates, this time with the cellulose nanocrystal substrate as the suspect. And there is some funding to acknowledge. So already from Chalmers times, Excellent Initiative Nano, BVSC has supported this. Some work was done with the European project, and then recently support from Academy of Finland was received. Thank you.
Thank you, Tiina, for a very nice presentation. We often get a lot of questions, but I also have the privilege to start. So the distance you found, if you go back some slides, one can see spots very regular. It's one slide more, I think it was.
Yes, here.
Yeah, this here. Was this the distance you expect between two C6 sulfonated groups, or is it one atom you see, or what is the yellow?
I guess what you expect then will depend how you expect your material to be constructed.
That is always true.
Yes, and also, of course, what is the level of the substitution here? Yeah. So I wouldn't maybe dare to go and say what I was expecting and what do we see. Of course, this is also kind of just the beginning. I mean, here we have, let's say if we go and we think about analyzing other materials than the CNCs with this method, we always need to think about the orientation of our material with respect to the beam and how can we see then those CNC highways, right? So I think there's quite a lot of more work to do to then say something very definitely about the structures.
But it is cool that you can see them. They seems to sometimes be very repetitive in in line. So so if you have Josephine, do we have a check on in the chat channels? And
I'm keeping track of them and trying to. Don't forget to raise. Yes, you can raise your hand also if you have any questions.
Absolutely. I have maybe a strange questions, but I had once a lab when I was a PhD student where we were measuring the diffusion constants for metal ions. So what do you have the same if you have the one charge and you have bigger and bigger ions, then the surface charge will decrease, I suppose. And I suppose that will also influence the water shell that it brings with it. So what influence do you think that the surface charge and maybe therefore the surface, at least how I remember the lab, which was the most awful lab I ever had as a teacher, but this as
a teacher,
that's also lost. But anyway, it was what do you think? Will the ordering of water have any influence when it comes to the interactions, and how do you think it interacts? What is your perspective on that?
That's a difficult question. I mean, it theoretically, So do you mean when we have already the cation, the hydration of the cation to the introduction of it?
Yeah, first when you just have them swimming around in the water, and then I suppose the water shell is different thickness. But
the hydration shell should be different. I mean, the size as well as then the hydrated size of the cations is different. But I don't really know. I mean, we still are thinking and trying to around it, but it should be different. I have not seen that it would then, I don't know what it would affect here.
No, I was just speculating if it could be so that if there were less surface charge, then they maybe water shell is easier to expel water when and it should interact differently with the sulfur group. I don't know. This is an open question. But that is nothing you have been. Maybe it was so stupid, so it was not.
No, it was not stupid. I just don't have an answer. We have been thinking, reading, looking into it. But I don't know what's the answer.
Anna has I saw Anna and Gerda. I think Gerda, do you want to say something, or I see?
They are forcing people to
very
ask
impressed
questions.
at Chalmers. Or should Anna? Can you unmute?
Yeah, Josephine already did. Can you hear me?
Yes, please, Anna, go ahead.
Thank you so much, Tiina. It was really nice to listen to the presentation. I was wondering on the same image that Annette was speaking about, just the first one you showed. Could one, because I suppose at least you say, okay, so we can see these sort of highways, and as you have the arrow, my eyes are immediately going align that arrow, but you could sort of put that arrow 90 degrees to the right, and there you would also see sort of.
You mean like
lines? Yes, exactly.
Yeah, exactly. Well, I mean, then we know where we have zoomed in, kind of, so we know how the CNC.
You know how the CNCs would
and
orient.
then here in this analysis, you can see that then Daniel was measuring with like the two directions.
Yeah. So this one would give you more sort of it would be more quantitative. This one. Yeah. Thank you. I think it's really cool that you can see it like this.
It's super cool. But if we go back to that, one of the lanterns interacted with light, whereas the other was interacting with the magnetic image resonance. Can you use this for, I suppose that maybe one can think that you could use it for diagnostics, but that maybe is not the first option. Are there other options you can think of when it comes to magnetic resonance?
Yeah, I mean, which one are you interested? I mean, with the light emission, the europium incorporated into cellulose materials. So there's quite a lot of research. I think it's then a matter of where it could actually be bringing the society something useful, right, to use it. And with the MRI, I mean, if it's it provides a contrast in the MRI, right? But I'm not sure if you would like to have a cellulose nanocrystal as a contrast agent, right?
No.
It would require quite a lot of other types of studies
yes,
to secure its use. So in a way, it's nice to observe that the gadolinium we can exchange it, or we can modify the cellulose with it, and it's clearly giving us what we want it to give. But if it's then practical, if it's a practical cellulose substrate, I don't think so. I mean, the CNC is very practical for this kind of investigation, but then for use, I don't think that it has what it takes.
I get your point. Mikael Shivas has a question also. Mikael, do you want to unmute and take it yourself?
There, I'm going down in the list. So
I don't know if you can hear me.
We can hear you perfectly, Mikael.
Yeah, I was just thinking about this cesium labeling of the CNC. If you can then use it to detect or check the orientation of the CNC if you have it embedded in a polymer matrix, like in a nanocomposite structure, because it is sort of quite relevant and interesting to see how reinforcement are oriented in composites.
Yeah, that's a cool idea. Then I don't know how to prepare the sample.
Because is this like a surface sensitive detection? You will see the surface.
Yeah, maybe the challenge is then I'm thinking of a composite where we have the polymer matrix and then let's say the cellulose filler is hopefully dispersed in a homogeneous manner, right? And we want it to interact.
Yes.
And then if we would label it with some heavier element and then analyze it, then if we look, let's say if we slice it and we look at it from one direction, we would need to be lucky to then find maybe the orientation that is useful for whatever we want to.
I guess it will be necessary to prepare the composite in such way so you have a high degree of orientation in the CNC already, so they are all, and then you sort of could confirm it.
Yeah.
but I don't know. Interesting option.
Yeah.
Thank you.
But I mean, with this kind of labels, I mean, they also are out there for some of the like visualization analysis already. So definitely it will work.
Okay. Very interesting. Thank you.
Well, thank you, Mikael, for the question. Josephine, how is it in the YouTube channel?
No, it's quiet there, so.
Okay, but I have some more questions, but I think maybe we should save the other ones and then we take them afterwards, Tiina.
Sure.
So
In November.
Tiina, you have taught me so much during the years when you were here at Chalmers, so I'm very happy that you did it once again. And I'm missing you a lot, as you probably know. But we're very thankful for the opportunity to listen to this. So thank you a lot, Tiina.
Thank you.
But you can stay and then I can talk a little bit more about my questions.
Sure.
So thank you for this webinar. Thank you, Tiina, again. Thank you, everyone who's been listening. The FibRe webinars will continue. It will be announced within the FibRe network, of course, and at Treesearch. So welcome back.
Yeah,
for next.
you're welcome. In April, I think it is, if I remember correctly.
So hope to see many of you there.
Yeah.
And it's open, Tiina, so you can join.
Perfect.
So,
Thank you.
Josefin, stänger du av så man kan...
no, I don't know.